Corresponding to every complex number, we associate another complex number known as its conjugate. Now, this conjugate is not only important on its own, but also helps us in proving and finding other properties of complex numbers. So, for example, properties of modulus of complex number. Now, let us first define what is conjugate of a complex number. So, given a complex number z is equal to x plus iota y, its conjugate, which is denoted by z bar, is equal to x comma minus y or x minus iota y. Simply, we can say that if I want to calculate conjugate of a complex number, then I will just replace this iota with minus iota. As an example, if I have complex number 2 plus iota 3, then its conjugate z bar is equal to 2 minus iota 3. Similarly, if I have another complex number z1, which is minus 4 iota, then the conjugate of this complex number z1 is z1 bar, which is equal to 4 iota. Now, what is the geometrical meaning of the conjugate of a complex number? Now, if I have this complex number z with components x, y, so this x, y means that x coordinate of this point is x and the y coordinate of this point is y. Now, what is z is equal to x, y? Then what is the conjugate of this z? This is in fact x minus y. Now, what is this point x minus y in this plane? So, the x coordinate is the same, but y coordinate, the sign of the y coordinate is changed. So, in other words, instead of going in the positive direction, now we are moving the same distance in the negative direction. So, this is z, then the conjugate of z is basically this point with coordinates x minus y. Now, it is a very simple observation that the distance from origin to this complex number z is the same as the distance from origin to the conjugate. In other words, we can say that the modulus of z and its conjugate are same. So, algebraically, it is very simple to prove. So, since modulus of z is x square plus y square, and we also know that if I calculate the modulus of z conjugate, which is in fact the modulus of x minus iota y, so this is going to be equal to x square plus minus y square, and we know that minus y square is the same as y square. So in other words, we can say that this is the same as the modulus of z. Now let us start proving some simple properties of conjugate. If I have two complex numbers z1 and z2, then the conjugate of their sum is the same as the sum of the conjugates. So the proof of this property can be done in the following way. So if I have z1 which is equal to x1 plus iota y1 and z2 is equal to x2 plus iota y2, then z1 plus z2 is equal to x1 plus iota y1 plus x2 plus iota y2. Now this is equal to x1 plus x2 plus iota y1 plus y2. And if I calculate the conjugate of the summation of z1 plus z2, this is going to be equal to x1 plus x2 minus iota y1 plus y2. So I can write down this number in the following way: x1 minus iota y1 plus x2 minus iota y2. Now we can see that this is in fact conjugate of z1, and this expression over here is basically conjugate of z2. Now on the same lines, we can prove the following properties of conjugate. Now I am leaving these properties as an exercise. Now we are going to relate complex conjugate with the real and imaginary part of this complex number. Now if z is equal to x plus iota y, and we know that real part of z is x and imaginary part of z is y, and conjugate by definition is x minus iota y. Now if I add z plus z conjugate, then iota y and minus iota y will be cancelled and I'll be getting 2x. So this implies that x is equal to z plus z conjugate divided by 2. So which means that the real part of complex number z is in fact z plus z conjugate divided by 2. And on the same lines, we can calculate z minus z conjugate. So in this case, x and x will be cancelled and we will be getting 2 iota y. This implies that y is equal to z minus z bar or conjugate of z divided by 2 iota. And this implies that the imaginary part of z is in fact z minus z bar divided by 2 iota. Now on the same lines, we can prove the following properties of complex conjugate, which is related to the real and imaginary part of complex number. And I'm leaving these two properties as an exercise. Now the next property relates complex conjugate and the modulus of this complex number. Now this property is true due to the following reason. So for this complex number, the modulus of z is in fact x square plus y square, which implies that square of the modulus is equal to x square plus y square. Now we also know that the conjugate of z is x minus iota y, and if I multiply z and z conjugate, then it becomes x plus iota y multiplied with x minus iota y, and this becomes x square minus iota square y square, and since iota square is equal to minus 1, so this becomes x square plus y square. So using this property, we can prove other properties of complex numbers. For example, we can prove that the modulus of the product of two complex numbers is in fact the product of the modulus of two complex numbers. So to prove this property, we observe that square of the modulus of z1, z2 is in fact can be calculated z1, z2 multiplied with z1, z2 conjugate using this property. Now we can multiply z1, z2 with the z1 conjugate, z2 conjugate, which is equal to z1, z1 conjugate and z2, z2 conjugate. Now using the same property, this expression is in fact the square of the modulus of z1, and this expression is square of the modulus of z2, and this implies that z1, z2 modulus is equal to the product of the modulus of z1 and z2. On the same lines, we can prove the following two properties of modulus of a complex number using this property which relates the conjugate and the modulus. Now we have seen triangle inequality, which gives us upper bound for the sum of two complex numbers. Now using these properties of conjugates, we can prove the triangle inequality in the following way. Now if I start from z1 plus z2 modulus square, now using previous properties, this is equal to z1 plus z2 multiplied with z1 plus z2 conjugate, which is in fact equal to z1 plus z2 multiplied by z1 conjugate plus z2 conjugate. Now if I multiply these two expressions, I will be getting z1 z1 conjugate, z1 z2 conjugate plus z2 z1 conjugate plus z2 z2 conjugate. So this is equal to, now this expression becomes z1 modulus square plus, now to simplify this expression, notice that if I write down this complex number as z1 Z2 mod as it is, plus, now this complex number can be written in the following form: Z1 Z2 conjugate conjugate, plus, now this expression is basically the square of the modulus of Z2. Now if we observe this expression, this is complex number Z1 Z2 conjugate plus the conjugate of this expression. So by previous property, this should be equal to 2 times the real part of Z1 Z2 conjugate, plus the rest of the expression remains the same. Now we know that the real part of a complex number is less than or equal to the modulus of this complex number. Now using this property, this is less than or equal to Z1 modulus square plus 2 modulus of Z1 Z2. Now here, instead of writing Z2 mod, I am writing Z2, since we know that Z2 conjugate modulus is the same as Z2 plus Z2 modulus square. So this expression is equal to Z1 plus modulus of Z2 square. So this implies that the square of the modulus of Z1 plus Z2 is less than or equal to the sum of the modulus and then taking square. And if I cancel these squares, because these are non-negative quantities, so I will be getting this inequality. Now using this inequality, we can calculate upper bound on this complex number in the following way. So z cube plus 3z square minus 2z plus 1 is less than or equal to z cube mod plus 3z square mod plus minus 2z mod plus 1. Now it is a very simple exercise to prove that if I take the modulus of the z cube, it is the same as the cube of the modulus. In fact, we will be using z1 plus z2 mod is equal to the product of modulus of z1 and z2. So using this, we can easily prove this thing. So this is in fact the cube of the modulus of z plus 3 square of the modulus of z plus 2 into modulus of z plus 1. Now since the modulus of z is less than 2, so this becomes, this is less than 2 cube plus 3 into 2 square plus 2 into 2 plus 1. So this provides an upper bound. So this number is basically an upper bound to the modulus of this expression. So this number is basically 8 plus 12 plus 4 plus 1. So this is basically 25. So 25 is the upper bound for the modulus of this complex number. Now we have seen what is complex conjugate, and we have seen that how this complex conjugate can be used to prove different properties of complex numbers.